Okay, explanation for this graph. These things are negatively charged, right? So they're going to be attracted to a positive. These things are positively charged, so they're going to be attracted to a negative. This has no charge at all. So it just goes straight on through. Doesn't care. And then the other thing I want you to discuss is why this differentiation is larger than that differentiation. Tiny, large. I don't know. Okay.
I don't get cars.
Yeah. Yeah, cows and chickens, sure. Gas field radiation detector. I would draw a little thing, I put this in here, put like a battery, and I put a counter. And I go over here and attach it, and then this thing is filled with argon. Some radiation comes in, smacks an electron off of here. That's negatively charged, leaving behind this argon that's now positively charged, which is weird. The electron hits the wire, goes through the wire, goes through the battery, gets counted, keeps going, and now it's at the exterior on this inside wall of this can where it reunites with its long lost argon, turning back into just argon. What can activate this? Just neutrons and gamma, not alpha or beta particles. They don't make it through the can. The alpha beta particles got read by the other type of detector we talked about, which was a scintillation detector. All right, so I got something. And then I got a person. And 120 here. They move back 15 meters. So this is 25, and this is another 15. So I got a person here. And so my equation would be, I go intensity 1, intensity 2, distance squared 2, distance squared 1. So intensity 1 will be equal to distance. All right, let's stop that. My sister's name is Michelle. 35 meters squared, 40, not 35, can't do math. Meters squared. And then the intensity was 120 millirem per hour. All right, so I've got 40 squared divided by 25 squared times 120. Yeah, that's totally wrong. I'm like, goes up, what? Oops. 25, 40. That's better. There we go. So my new intensity at this distance is 40, I'll say 47 millirem per hour. But this was gamma, and I shoved 4 inches of lead in between. So each 2 inches is 1/10 thickness. I have 2 of those. So what do I do with my 47 number? I move my decimal place over. From here, go to there, and go to there. So my actual answer is my new intensity is 0.47 millirem per hour. Why what? Why'd I move the decimal place? Because there's lead shielding in between me and it. because 2 inches of lead is 1/10 thickness, and there's 2 inches twice, so I move the decimal place twice.
Probably doesn't matter for the significant figures question.
Definition of half-life. What do you got? So half of its atoms decay and turn into something else. Um, 2048, cobalt 60, half-life. How long does it take to reach that? Okay, so time is equal to negative 5.27 years divided by natural log of 2, natural log of 256 divided by 2048. So negative 5.27 divided by ln2 close parentheses ln 256 divided by 2048. Looks like 15.81 years. Is there a way you could do a quick check on that? See if that is reasonable. Well, you could say I've got 2048, right, grams here, and time equals 0. And then I cut that in half, and half of that is what? And that's going to be 5.27 years. And then I cut that in half, and I get 500 and what? And so that's going to be 10.54 years. And then I cut this in half, and I'm at 256. And so this should be 15.81 years. Why does that work out for me?
That's wrong.
48, yeah. Just because I put up numbers that are easily divisible by each other, they're the numbers that people use for computing power, right? 256, 512, 1024, 2048, no? Down on that tie? That's okay. Okay, so what do you need here? 3 things. What? No. What? Yeah. I need a magnetic field. What else do I need? No. I need a current carrying conductor. Could be anything that carries current, but a wire would be easiest. And I need relative motion between the two. What does that mean? So here's a current carrying conductor. Are we okay with that? So if I take this wire and I have sure. Let's say this is a bar magnet. I can do this, and that would cause electricity to be generated. Or I could do this. I just have to have, somebody's got to be moving. That's it. I mean, I could do this, but that would make an engineering nightmare. So I just move one of them around. All right. So as humans, that's how we, with the exception of solar power, that's how we create electricity is. I got a wire, I got a magnetic field, and I move one of them. Yeah.
Well, isn't that only inducing electricity? Is that how that works in a chemical battery?
No, it doesn't work like that at all in a chemical battery.
Okay, so this is just having induced electricity.
How do you create electricity? I mean, electricity is electron movement, and I just made electrons move. So it's electricity.